Almost everyone that has worked with JavaScript has heard of the V8 engine, the idea of the JavaScript engine. And most people know that JavaScript is a single-threaded language, that it uses a callback queue. You may also hear phrases like JavaScript is an interpreted language. Let's tackle what that means over the next couple of videos. What is this engine that we speak of? Well, if I write some code, like let's say const is happy equals to true. Well, we just wrote some JavaScript. I'm assigning the true boolean to the variable is happy. Now, how do we read this? Or how does the computer read this? Imagine if somebody comes up to you and gives you a computer and they tell you, hey, tell this computer to display a picture of horses on the screen. And you start looking at this computer and you tell the computer to display an image of a horse or horses in French. Is the computer going to understand you? No, the computer would have no idea what you just said. In similar fashion, if I gave a computer with a CPU a file that is a JavaScript file, and I tell it, hey, read this file and do something for me, well, the computer only understands ones and zeros at the end of the day. And when we give it the JavaScript file, it's like me talking to a computer in French and the computer being like, what? What are you talking about? Plus, talking to a computer in French, well, people are going to look at you like you're a crazy person. So the computer doesn't really know what JavaScript is. So how are we able to communicate using a JavaScript file so that the computer displays pictures of horses? And this is the first step in our learning, and that is the JavaScript engine. By having a JavaScript engine right over here, it allows you to give this machine the JavaScript file, and this machine is going to understand this file and tell the computer what to do to display pictures of horses. In a sense, you just created a translator, so you can communicate with somebody that doesn't know your language. And this special engine, called the JavaScript engine, understands JavaScript. Our computer finally understands us because of this JavaScript engine, and it says, I'm on it, boss. I'll start displaying those horse pictures. There you go. That's our first step. And over the next couple of videos, we're going to talk about exactly what's happening inside. But do you think there's one JavaScript engine or many JavaScript engines? Well, as you can see from this Wikipedia list, there are a ton of engines. And they're called ECMAScript engines, and we'll get into why that is later. But these are all the JavaScript engines. Some of them you may have heard of, like V8 or SpiderMonkey or Chakra. So anytime we use an engine, we're able to give it a JavaScript file. And this JavaScript file gets understood by the engine, and it allows this engine to communicate and tell the machine, the computer, to do what we ask it to do with JavaScript. Now, these engines are written by programmers. For example, V8 engine is written in C++. But why do people write these engines? 2008 marked a really pivotal moment in history when it comes to JavaScript, because V8 was released by Google. Before then, most browsers used engines that were very basic, which meant that JavaScript was a little bit slow. You see, Google had this problem. They had something called Google Maps. And Google Maps, as you know, requires a lot of power. It does a lot of things. You can ask it for directions to zoom in and zoom out, maybe even use Street View. And all the previous engines before it would make Google Maps very, very slow on the browser. And Google, because they're a search engine, they want everybody to use their search engine. And they built a browser in order for them to control more of the market. So with Google Maps and their own Chrome browser, they said, we're going to write our own JavaScript engine, the V8 engine, so that JavaScript runs way faster on the browser than it's done previously. And in 2008, they released V8. But the big takeaway for us here is that really, really smart people work on these engines so that our JavaScript runs as fast as possible on the browser, on the server, or any type of computer. So every day, JavaScript gets faster and faster for us because of the work that goes into these engines. Okay, but what is inside this engine, this magical machine that understands JavaScript? It reads our code and then it runs this code. Let's get into that in the upcoming video. Bye-bye. Here's a fun little question. Who do you think created the very first JavaScript engine? Just pause and think about this. Give up? Well, the first person to create the very first JavaScript engine was its creator, Brendan Eich. This man right over here. While working at Netscape, which became the first commercially available browser, he created the early version of what became to be known as SpiderMonkey, which is what Firefox still uses right now as their JavaScript engine. And Brendan Eich was the very first person who created the language JavaScript to implement this engine so that you're able to run JavaScript on a browser that previously could only read HTML and CSS. Fun little fact for you. All right, let's get back to the videos. Welcome back. So we know that this thing called the JavaScript engine takes our written JavaScript code and does some magic to tell the computer to do what we want it to do. So what's happening inside of this engine? And here's the tricky part. As we know, this engine can be built by anybody. Yes, that means you can build your own JavaScript engine. But it's a lot of work. And at the end of the day, it's just a program. And the V8 engine, which is the most popular, most common, and some would say the fastest JavaScript engine that the Chrome browser and Node.js uses, which we'll talk about later on, this engine is written in C++, a low-level programming language. But let's see what's actually happening inside here. Inside this engine, it looks something like this. We give it a JavaScript file, and first it does something called lexical analysis, which breaks the code into something called tokens to identify their meaning so that we know what the code is trying to do. And these tokens are formed into what we call an AST, that is an abstract syntax tree. So we parse the code, that is, we try and figure out how the text is divided up based on keywords from JavaScript, and it gets formed into this tree-like structure called abstract syntax tree. And there's a fun little tool online that you can use to demo this. If we go to astexplorer.net, it'll show you how this abstract syntax tree looks like. And you have a bit of code here, and as you can see, you can look at it in JSON format, or you can use the tree. And it breaks down the program into different things that are happening. We have a variable declaration, a declarator, and although this may look like gibberish right now to you, this allows the engine to understand what's going on in the program, or at least break things down one by one. And once in this form, it goes through something called an interpreter, profiler, compiler, and we get some sort of code, which we're going to talk about later on. And this whole engine is going to spit out some code that our CPU on our computers is going to understand to give it instructions. And you can think of this whole process, again, which we're going to talk about in more detail coming up, as something like this. We can create our own JavaScript engine by saying function, and let's say JS engine function that takes in some code, and this code is going to return for us, let's say code.split, and we'll use some regex here just to split up our code. And now if I write some code here, let's say JS engine, and we give it our code, which will be a string that says variable a equals to 5. Look at that. We've created a simple engine. I know, there's a lot more complexities to it than that. But that's what it's doing. We're giving it a piece of code, which just gets stringified. And then it tries and breaks things down into different parts so that maybe in this function, we can say, if you see variable keyword, that means whatever comes after it is a variable that we're going to assign, and so on and so forth. But you might see a problem here. What problem or problems do you see with everybody creating their own engines in JavaScript? Just like we did, right? Can't we just create our own engine and all of a sudden, boom, there it is. We have our JavaScript engine? Well, yes, you can definitely do that. But remember our list over here, how it was called ECMAScript engines and not JavaScript engines? That's because if everybody can just create a JavaScript engine, it'll just be total chaos. Which is why ECMAScript was created. It tells people, hey, here's the standard and how you should do things in JavaScript and how it should work. And ECMAScript is the governing body of JavaScript that essentially decides how the language should be standardized. So it tells engine creators, this is how JavaScript should work. But internally, how you build the engine is up to you as long as it conforms to these standards. And if we go back to our example over here, this engine, inside of this box, as long as it conforms to ECMAScript standards, I can do whatever I want as an engine creator. So companies and organizations are battling to have the fastest engine so people use their tool. For example, Google is really interested in having the fastest engine so that more people use their Chrome browsers, so that they use their search engine, so that they can sell more ads and make more revenue. But keep this in mind, that this can be implemented any way we want, and it constantly changes to find the fastest way possible to have JavaScript work in our browsers or even outside of our browsers. And we're going to be talking about the V8 engine here because it is the most popular. And you might see some different variations of this. But what we're going to talk about here applies to most JavaScript engines. And although things may change over time, as long as you understand the principles and why it's built the way it is, we're going to be able to understand how to write optimized code. But before we get into that, let's talk about what these things are. We have the interpreter and the compiler. I'll see you in the next video. Bye-bye. Welcome back. Let's talk about interpreters and compilers, which, as we can see, are important pieces in our JavaScript engine. You see, in programming, there are generally two ways of translating to machine language, or something that our computers can understand. And what we're going to talk about here actually applies to most programming languages, not just JavaScript. Python, Java, C++, any language you can think of is going to use some of these concepts. So it's very important. Let's start with the first one, the interpreter. With an interpreter, what we do is we translate and read the files line by line on the fly. Let's have a look at how this works. I have a piece of code here that, doesn't do very much, does it? I have a function that does some calculation, and we just loop over this calculation, which is 5 plus 4, right over here, and we do that, 1,000 times. That's a long time. And you see that we get the result, 9 over here. But the loop is happening over and over. So if I go console.log, here, we see that, this is looping over and over and over. Now, with an interpreter, if I give this file to an interpreter, the translation happens line by line on the fly. And this is how you think the code should be run, right? The interpreter sees the first line, then the second line, then the third line, and says, all right, this is a function. And then it goes to the next part and says, all right, I should loop over this a bunch of times and it starts doing some calculation. It's going to go and see, all right, that's what the function is. I'm going to run 5 plus 4. And then I'm looping again. So I'm going to go once again, run some calculation 5 plus 4, some calculation 5 plus 4, and it keeps running, keeps running, keeps running. And this is how you might think code should be run, right? Because interpreting code simply means taking a set of instructions like we have over here and returning an answer and doing something with that code. It's just like me telling a computer to do this, then do that, then do this. And initially, that's how JavaScript worked. It was interpreting using an interpreter, which makes sense. All right, but what about a compiler? What's the deal with a compiler? Well, a compiler, unlike an interpreter, doesn't translate on the fly. What it does is it works ahead of time to create a translation of what code we've just written, and it compiles down to usually a language that can be understood by our machines. Let's have a look at this in more detail. With a compiler, this time around, it's going to take one pass through the code and try to understand what the code does. And it's going to take the program in JavaScript or any type of language and write a new program in a new language. Let's say to programming language Y or X. And this language that it spits out, let's call it just X. Well, this language that it spits out, if we interpret it, this language that is going line by one at a time and running it, it's going to create the same results as our previous language. So a compiler tries to understand what we want to do and takes our language and changes it into something else. And this usually happens into something called a lower level language, such as machine code. Now, I know you're still a little bit confused. You see, the definition itself is actually a little bit fuzzy. In some respects, all languages have to be interpreted and compiled. Because it has to run, it has to be interpreted, and it also has to most likely get translated into something low level like machine code. For example, we have a high level language here like JavaScript, and we run a piece of code here. An interpreter will take this code line by line and spit out bytecode like this that will execute this code for us. Or a compiler might take this code and go through this and spit out machine code, just like that, so that it can give it to a CPU so that the CPU can actually run the code. But remember how I said a program or most languages are both compiled and interpreted? Because over here, x86 code, which is machine code, this is handed off to the CPU and it needs to interpret these instructions. And in reality, when it comes to x86, it's actually too slow to be interpreted literally. So instead, most modern CPUs will compile this x86 code into its own native microcode. So as you can see here, there's a lot of layers that happen on and on. But the main takeaways is this. There are two ways to run JavaScript, using an interpreter or a compiler. Now, I know it's still a little bit fuzzy, but if I ask you, why would we want to do one over the other? What are the pros and cons on each? What do you think that is? Why would you pick one over the other? In the next video, we're going to explore that. I'll see you in that one. Bye-bye. Welcome back. Let's have a look at the pros and cons of each. First off, interpreters are quick to get up and running, right? Because if we go to our example, with an interpreter, we don't have to convert this into another language like language X, like I showed you with a compiler. There's no compilation step before you can start running your code. You just give this to an interpreter, and the interpreter starts translating their first line and just runs the code for us. Because of this, an interpreter is a natural fit for something like JavaScript, right? A JavaScript file gets sent from the server to the browser, to the client on the front end, and we want that JavaScript to execute right away because our users are going to be waiting on the web page trying to interact with our application. And JavaScript originally was created for the browser. So being able to interpret JavaScript and run it as fast as possible, well, that was ideal. And this is exactly why JavaScript used interpreters at the beginning. But there's a con with using an interpreter. And this is the same problem that Google had back in the day when they had Google Maps, running a lot of JavaScript, but it'll get slower and slower and slower. Because the problem with interpreters is that when you're running the same code more than once, for example, if you're in a loop like this one over here, where we're running this piece of code over and over and over, even though it gives us the same result, it can get really, really slow. The compiler actually helps us here. It takes a little bit more time to start up because it has to go through that compilation step at the beginning, go through our code, understand it, and spit it out into another language. But the compiler will be smart enough that when it sees code like this, and this is obviously a simplified version of it, but if it sees code like this that we just loop over and it has the same inputs, returning the same outputs, well, it can actually just simplify this code. And instead of calling this function multiple times, can just replace this function with something like 9, because we know that we want to return 9. Because a compiler doesn't need to repeat the translation for each pass-through in that loop, the code generated from it is actually faster. And these sort of edits that compilers do are called optimizations. So let's go back to that question. Interpreter or a compiler? Which one is better? Well, they both have their pros and cons. Compiler obviously takes a little bit longer to get up and running, but the code is going to eventually run faster. Or interpreter, that is really fast to get up and running, but unfortunately doesn't do any optimizations. Is there a way that we can get the best of both worlds? And this is what some engineers came up with in late 2000. And if we use Google as our example with the V8 engine, what if we combine the best of both worlds? What if instead of using the compiler and interpreter, we combine these two and create something called a JIT compiler, or just-in-time compiler? And this is exactly what browsers started doing. Browsers started mixing compilers, specifically these JIT compilers, for just-in-time compilation to make the engines faster. So let's see how V8 engine does this underneath the hood in order to use the best of both worlds. Remember, we parse the code, we turn it into an abstract syntax tree, and then this code initially goes to an interpreter. And by the way, again, I'm showing you what the V8 engine does. There's small changes in different engines, but this is probably the best, most optimum way to run the JavaScript engine as I'm recording this video. Initially, the code gets sent to the interpreter. And in the V8 engine, this is called ignition. I know they have really cool sounding names to make them sound like they do things fast. But this interpreter in the V8 engine is called ignition. And it takes this AST and it spits out bytecode. And remember, bytecode is code that's not as low level as machine code, but it's code that is able to be interpreted by the JavaScript engine in order to run our programs. So that's the first step. But then we see over here that there's something called a profiler, this old man that's checking out our code. And this profiler, also called a monitor, monitors and watches our code as it runs, it makes notes on how we can optimize this code, such as how many times it is being run, what types are used, and how we can possibly optimize this. And using this profiler as the code is running through our interpreter, which tells our browser what to do, if the same lines of code are run a few times, we actually pass off some of this code to the compiler, or a JIT compiler, or just-in-time compiler. Because as the code is running, the interpreter is going to say, hey, here's some code for you to optimize. Passes it off to the compiler. And the compiler, as the application is running, takes the code and compiles it or modifies it so it does what you ask it to, but trying to make optimizations so it runs faster. And it then replaces the sections where it could be improved of the bytecode with optimized machine code. So that code, that optimized code, is used from that point on instead of the slower bytecode. So it mixes and matches things, and it constantly runs through this loop. And this means that the execution speed of JavaScript code will be improving, right? This means that the execution speed of the JavaScript code that we entered into the engine is going to gradually improve, right? Because the profiler and the compiler are constantly making updates and changes to our bytecode in order to be as efficient as possible. So interpreter allows us to run the code right away, and the compiler and profiler allows us to optimize this code as we're running. That's where the name comes from, JIT compiler, just-in-time compiler. And this compiler for V8 is called Turbofan. Again, a cool sounding name to make it sound like things are going fast. And by the way, just a bit of a fun fact. Previous versions of V8 engine actually used 2 JIT compilers with really cool sounding names, but they changed it to this method because there were some faster optimizations that they could do. So why do we just learn all of this? You can write JavaScript without knowing any of this stuff and you'll be fine. Now that we know how the engine works underneath the hood, we can write more optimized code. Code that the compiler can take and run it faster than our regular JavaScript. And we also can use this knowledge to make sure that we don't confuse the compiler, because the compiler isn't perfect. It can make mistakes and it can try to optimize code that actually does the opposite. And if it makes a mistake and it does something unexpected, it does something called de-optimization, which takes even longer time to revert it back to the interpreter. So by learning this, we're going to have a video coming up where we learn how to write optimized code so that we help out this profiler and compiler to make sure that we're able to run the fastest code possible. And let's learn those optimizations. But first, let's talk about something quickly. I'll see you in the next video. Bye-bye. I wanted to do a quick video to see how what we just learned applies to different languages. For example, you might have heard of an executable file. That is a .exe file, especially if you've ever used Windows before. You double-click a file that ends in .exe, and then the code starts running. The application starts running. And that .exe is an executable. And most of the time, these .exe files are created by C++. You write a C++ code, and you compile it to a .exe file. For example, you can use a command like g++ your program .c++. So that's your C++ file. And you're going to output it to an executable, your program. And this is going to create that .exe file that you compile down from C++ to an executable machine code. So that when you double click a file that is your program, it's going to run because it's been compiled. Now, when you use a program like, let's say, Java, on the other hand, uses something called the JVM or Java Virtual Machine, where it compiles your code or interprets your code to bytecode inside of this JVM. And this Java Virtual Machine is going to understand this bytecode. So unlike a compiled language that has to be compiled for each specific type of computer, a Java program only needs to be converted to bytecode once. And that bytecode can be understood by the Java Virtual Machine. And that's where the term for Java, write once, run everywhere, came from. Now, one thing to note here is that bytecode is not a native machine code. That is, most computers won't understand this bytecode. They might understand machine code, but not bytecode. So with bytecode, you need software, such as the virtual machine or a JavaScript engine, so it can execute it directly. I can't double-click a bytecode file and run it without an engine or a JavaScript machine. So I have a question for you, knowing what you just learned now. Is JavaScript an interpreted language? You'll hear this a lot. JavaScript is an interpreted language. But learning what you just did, is JavaScript an interpreted language? I mean, yes, initially, when JavaScript first came out, you had JavaScript engines such as SpiderMonkey, created by Brendan Eich, that interpreted JavaScript to bytecode, and that engine was able to run inside of our browsers to tell our computers what to do. But things have evolved now. We don't have just interpreters. We also use compilers to optimize this code. So this is a common misconception. When somebody says JavaScript is an interpreted language, yes, there is some truth to it. But it actually depends on the implementation. You can make an implementation of JavaScript, of the JavaScript engine, that perhaps only compiles. And by the way, this is also true when it comes to something like Python. Python can be run through a compiler, or it can also be interpreted, even interpreted through something like the Java Virtual Machine. So it all matters depending on implementation. So the next time somebody tells you, hey, JavaScript, that's an interpreted language, you can sound super smart and nitpicky by saying, well, not technically. Technically, it depends on the implementation. All right, I'll see you in the next video. Bye-bye. Welcome back. Why do we just learn all of this? Well, because now we know a critical part in being a JavaScript programmer. We want to write code in a way that helps the compiler make optimizations. We don't want to work against it and make things slow. Throughout the rest of the course, we're going to learn different ways to write efficient code, but I want to give you some basic things to watch out for when working with JavaScript engine. Now, keep in mind that most of these things I'm going to show you will seem like things you don't really use or see that much anymore. And that's because most developers don't use them since they can be bad for optimizations. But it never hurts to know what they are. It doesn't mean that you should never use them, but that the use cases for them are very rare. So here's the list. In order to help the JavaScript engine, we want to be really careful with these on the left. Functions that call literally the eval function, which comes with JavaScript, can be very problematic. Arguments, which we're going to talk about when we get into functions of this course, something that comes with every function. There are many ways that we can use this keyword by JavaScript, but there are many ways that makes compilers unoptimizable. So we have to be really careful with using arguments. And I'll show you later on how we can use parameter destructuring to avoid using arguments. For in loop, for example, when looping over objects, can also be problematic sometimes. So I like to use object.keys and iterate over the object keys that way. The with statement, which once again, you don't see very often in the wild anymore, is another problematic one. And also the delete keyword in JavaScript can be problematic. Now, I'll leave resources for you to read up on them if you really want to get into the weeds. But there's two main things I want to talk about here that are the main reasons that these things in JavaScript can make our code less optimized. Let's have a look. The first thing I want to talk about is something called inline caching. And inline caching we can demonstrate this way. Let's say we have a function, and this function will say find user that takes in the user parameter. And this function will just return a template string. We'll say found, let's say user.firstname. Then last name. And here we can just create an object, call it user data, that will have the first name, say Johnson, and last name, say Junior. Now, all we do here is say find user and give it the user data object. Now, inline caching does something really interesting. Due to inline caching done by the compiler, code that executes the same method repeatedly, that is, let's say the find user method or function was being called multiple times, well, the compiler can optimize this so that whenever it's looking for the user data, which has first name and last name, it can use something called inline caching, where instead of looking up this object every time, finding the key, that is first name and last name, and then their values, it will cache or inline cache so that find user just becomes this piece of text. So if we call find user over and over and over, we would just replace that with found Johnson Jr. Because at the end of the day, that's all that the function is doing. The other one that is really important for optimizing compiler code is something called hidden classes. And a lot of the gotchas that I showed you previously, that is this one over here, such as the delete keyword, really affects this hidden classes when it comes to compilers. Let's have a look. If I had a function, let's call it animal, that receives x and y parameters, and we'll use the this keyword for now. We're going to learn more about that soon in this course, don't worry. But let's say we just have this animal with x and y properties. And now we create a new object. Let's say const object1 is going to be a new animal that takes in 1 and 2 as the properties. Doesn't really mean much, but there's our first object. And then our second object will do the same thing, but this time with different parameters, 3 and 4. Now, a compiler is going to take a look at this and say, all right, we have an animal that we're creating here, and we're assigning it to object 1 and object 2. But if I go ahead and add object1.a to equal, let's say, 30, and then object1.b to equal 100, and I'll do the same thing for the object 2, except that this time around for object 2, I'm going to create it in different order. So that is, I add the B property and then the A property to object 2. Hopefully that's not too confusing. That code is actually going to make the compiler run slower or de-optimize the code. And that is something called hidden classes. You want to try and instantiate your object properties in the same order so that hidden classes, which is what the compiler uses underneath the hood to say, oh, this animal class, this object 1 and object 2 objects have the same hidden class. That is, they have the same properties. But as soon as you start introducing things in different orders, it's going to get confused and say, they don't have a shared hidden class. They're two separate things. And internally, that's actually going to slow things down. So one thing you want to do in a situation like this is to assign all properties of an object in its constructor over here. So that is to add the A and B property in here so that you avoid this issue. Or making sure that we add things in the same order. And that's why there's this issue of delete keyword as well. If I delete the property here of the object, well, again, I changed the hidden classes so that they don't match up anymore. Now, when it comes to optimizing the compiler, there's small little gotchas like that you don't really have to worry too much about it. The key takeaway from here is that we should write code that is predictable, not only for humans, but also for machines. The more predictable your code is, the better it will be because it'll have no surprises. And throughout the course, we're going to learn these practices that will help us write optimized code that is predictable and that doesn't confuse the compiler. I'm not going to mention every single time that we're doing an optimization for the compiler. We're just going to assume that these best practices, when incorporated like I'm going to show you throughout the course, it's going to help us write fast, efficient code. I'll leave resources for you here if you want to learn a little bit more about this topic and really get into understanding what this hidden classes is. It isn't something that you need to worry about too much. But for now, I'll see you in the next video. Bye-bye. Here's another test for you. It may be something that you've been asking yourself throughout these past couple of videos. If we have to do all this interpretation and compiling of the language, why not just use machine code from the beginning? Why don't all programs just use machine code ahead of time? We compile our code, let's say JavaScript, and then we just give our websites our machine code. So they don't even have to worry about all this compiler interpretation and JIT compiler. What do you think the answer to that is? Take a second here, pause the video, and see if you can answer this yourself to test your comprehension. All right, you ready for this? You see, if JavaScript were compiled, then either compilation would have to be super fast, because remember, our JavaScript files get sent from the server to the browser. So the compiling has to happen on the browser, or the competing browsers, that is Firefox, Microsoft Edge, Chrome browsers, would have to agree on some binary executable format or standard that can understand this machine code. Because at the end of the day, these browsers are the ones that are executing the code. Now, when JavaScript was created in 1995, that's the start of the browser wars, where browsers are competing against each other. So compiling the code ahead of time, or even just compiling the code on the browser, was not feasible at all because back in the day, that was really, really slow. But also, having all the browsers agree on an executable format to run JavaScript, well, they didn't get along, so that was going to happen. Even now, browsers have different ways of doing things, and there's just no real standard. But luckily enough, things might change in the future. We now have something called WebAssembly, and something that you should really keep an eye on because this could be a game changer in the future. We have the standard binary executable format called WebAssembly. And this is what we didn't have in 1995. We didn't have the competing browsers agreeing on this format where we can compile our code all the way down to WebAssembly, this executable format, so that it runs really, really fast on the browser instead of having to go through that entire JavaScript engine process. So keep an eye on WebAssembly. But I hope now, if you've heard about WebAssembly and you're curious what it is, that's the big advantage of it. We might not have to do all these interpreter, compiler, and all the steps that JavaScript requires to actually run the code on the browser. All right, I'll see you in the next one. Bye-bye. Welcome back. Up until now, we've talked about topics that are definitely important, but they won't really affect your day-to-day coding. And you won't get really asked about what we just learned about interpreters and compilers in an interview. But starting in this video, we're going to learn about something that will come up again and again in your career that's very important and foundational to JavaScript that any senior developer should know. And it's also something that we're going to keep bringing up over and over throughout this course. So make sure you pay attention. And up to this point, you might have wondered why I ignored completely this little pink and orange box, the call stack and the memory heap. And good, you've been paying attention because we're going to talk about this over the next couple of videos. You see, we learned that the JavaScript engine does a lot of work for us. But the biggest thing is actually reading our code and executing it, right? And what do you think the two most important things in this step are? That is, one, we need a place to store and write information. That is, to store our variables, our objects, our data of our apps. And a place to actually run and keep track of what's happening line by line on our code. Well, we use call stack and memory heap for that. We need the memory heap as a place to store and write information, because at the end of the day, all programs are just read and write operations. That way we have a place to allocate memory, use memory, and release memory, that is to remove it, just like these cupboards over here. And two, with the call stack, we need a place to keep track of where we are in the code so that we can run the code in order. And with these two things, the JavaScript engine is able to do that. So to review, the memory heap is where the memory allocation happens. And the call stack is where the engine keeps track of where your code is in its execution. But enough diagrams, let's actually show you an example. When we look at call stack and memory heap, well, if we write a simple const number equals 610, what we're saying here is please allocate memory for the number variable and make this number variable point to, in memory, in our memory heap, the value 610. If we do, let's say, a string, it's the same thing. We're going to tell the engine to, hey, please allocate memory for a string variable. So now, whenever we use string, we can say, oh, go into our memory. String is pointing to somewhere in our memory to this value of some text. Another way to think about it is if we have an object that is going to equal first name is going to be Andre, and last will be my very confusing last name that nobody can pronounce, Nagwe. And all we're telling the computer here is saying allocate memory for an object and its values. So now we're telling the JavaScript engine, hey, I'm going to assign this human variable, and this human variable is going to point, anytime I call it, to a region in memory, in our memory heap, that has these values. The first and last key that point to Andre and Nagwe values. To review, our memory heap is simply a free store, is a large region in memory that the JavaScript engine provides for us, which can be used to store any type of arbitrary data in an unordered fashion. There's no order to this memory. It just allows us to use variables to point to different storage areas, just like a little cupboard here. And a lot of science goes into optimizing the way space is allocated here, but we don't need to worry about that. We know that the engine takes care for us to put data into storage boxes for us. And that's pretty easy, right? Memory heap is not that hard. Just a place for us to store our information. But what about the next one? Call stack. How does that help us? Well, if we go back to our code, let's write some code here and we'll create something very simple. We'll have a function that will be called calculate. And this function will have a sum total that does some random calculation like 4 plus 5. And it's going to return sum total. It's going to return 9. So as we know, this function is going to be allocated to memory so that anytime we call calculate, it's going to look in memory and see, oh yeah, calculate, I have it right here. Here, run this piece of code. And every time we run this code, calculate, we use the call stack. So we can think of call stack as a region in memory which operates in first in, last out mode. What does that mean? Well, when we run calculate, we simply, on our call stack, it's going to just add the calculate function on top of the stack. And after we finish running this function, it's going to remove it. Now, to make this a little bit clearer, let's add another function to here, and then we're actually going to run this in Google Chrome to show you what's happening. I'm going to create another function called subtract 2, and it's going to take a number as a parameter, and we're going to just return num minus 2. Just going to subtract 2. So that in our calculate function, we can just return subtract 2 and give it the sum total. So it's going to subtract 2 from 9. So it should give us 7. Now, let's see how the call stack is going to work when we run this function. I'm going to copy this and go to our Google Chrome developer console. Now, I'm going to click on sources here, and you might have to click on this arrow to go to snippets. And I can just add a new snippet here. And as you can see here on the right-hand side, I have something called call stack that will show us what's happening. If I copy and paste this code, let's see what the call stack does. I'm going to add a debugger statement in here, which is going to pause the execution right here before I write calculate. And let's hit run and see what happens. All right, we've paused our execution, as you can see here, before we've done calculate. So the JavaScript engine has gone through this piece of code. I see that, okay, we've declared our functions. The JavaScript engine knows what subtract 2 and calculate is, and it has some place in memory that it stored this information, but we haven't run anything yet. But on the call stack, I see something called anonymous here that we didn't see before. What is that? Well, that's the global execution context, and it's something that we're going to talk about in the next section. But for now, it's anonymous because there's no name for this file. This is the JavaScript engine saying, hey, I'm running this file. This is the first item on the stack, and the first action that we take is to run this file. If I click on this down arrow, we will see that we get to calculate. That's the next step in the JavaScript engine. And if I click down again, see what happens to call stack here. The calculate function just got pushed on top of the stack. So our call stack now has the anonymous function, which was the global execution context, which was the main run of our file. But now, because we've run a function, we're inside of this function now. On top of the call stack, we have calculate. If I go next, I see that I've calculated the sum total, and the next line is going to be subtract 2. See what happens to the call stack here. If I click next, we're now inside of subtract 2. Another function was called, and we push another item on the stack. Now, here's the interesting part. We are not done with the calculate function, are we? We're still inside of this calculate function, and because this calculate function called subtract2, we're now inside of subtract2. I know, kind of confusing, kind of like Inception, but that's what's happening here. The call stack tells us, hey, right now, where are we in the code? Well, we're at subtract2. Once we're done with subtract2, then we can go back to calculate. And then once we're done with calculate, then we can go back to the global anonymous function, which is what happens in line 11 here once we finish our work. So watch, if I click next, the subtract2 is now going to return num minus 2, and the call stack, the subtract2 gets popped off the call stack. We're now at calculate, and we have sum total, which is 9, and we know what subtract2 is. That is num minus 7. So if I go next, calculate gets returned, and if I go next, we're done with the function. Look at that. Our answer returned 7. And that's what a call stack does. The call stack stores functions and variables as your code executes. At each entry, state of the stack, also called the stack frame, which is the frame over here, these 3 stacks, allows us to know where we are in the code. And it runs in a first in, last out mode. That is, the first one in is the last one getting popped out. And we can keep adding to the stack, and eventually it pops all the function calls until we are done with our commands. And we use the memory heap to actually point to different variables and objects and data that we store so that we know where to look. And by the way, this is the way it works in most programming languages. We have call stacks and memory heaps. And these are the 2 locations that JavaScript remembers items. Now, since every JavaScript engine has different implementations, where variables are allocated is not 100% the same all the time. So a good way to think about it is this. Simple variables can usually be stored on the stack, and we'll learn about this later on. And objects, complex data structures like objects, arrays, and functions, which we're going to talk about, are stored in memory heaps. The cool thing about call stacks is that it allows JavaScript to know where it needs to be in the code. Whatever is on top of the call stack is where JavaScript is running. How genius is that? One last thing. If we go back to the function that we had, and let's say this time around, we're just going to return sum total and not going to use subtract2 function at all. Instead, we're going to run calculate twice. What do you think is going to happen? Well, if I run this code, we have our global execution context. We hit next because a new function was called. We added to the stack on top. There we go. And now we run through this code and we return 9. And the call stack calculate function gets popped off. We're done with the function. And then we go on to the next line, which is line 11. And once again, we call this function. As soon as we call a function, it gets popped or pushed onto the stack. It runs through the code and then returns. And it gets removed from the stack. All right, we've gotten that part. Now let's get into a fun video where we try and break this and cause a stack overflow. I'll see you in the next one. Bye-bye. Welcome back. Let's try something fun. What happens if we keep calling functions nested inside of each other over and over and over? We saw in the previous video with the calculate function, if you call calculate line 10, then line 11, then line 13, this stack is going to get pushed on and then popped off, pushed on and then popped off. But what if we have functions that are nested inside of each other so that we keep growing this stack until it gets larger and larger and larger and larger and larger until we can't do it anymore? Well, that's called Stack Overflow, just like the name of a very popular website for developers and programmers. And Stack Overflow can be caused very easily. Let's have a look. All we need to do is create a function. Let's call it Inception. And this function will just call itself. I know that looks confusing. And what we're using here is something called recursion. And recursion is a function calling itself. There are some cases where things like this, recursion, is quite useful. But that's something beyond the scope of this course, and it's something I teach in my other courses for data structures and algorithms. But recursion is one of the most common ways to create a Stack Overflow, or a lot of functions nested inside of each other to create that stack that keeps growing and growing and growing. In this case, if I run Inception, it's going to keep adding things onto the stack more and more and more. So what do you think happens if I run this? Well, I get a maximum call stack size exceeded. We actually get a stack frame of what the error is. At each entry, the state of the stack, also called the stack frame, is shown. If at any function produces an error though, JavaScript is going to print this stack trace, which is simply a snapshot of code execution at this stack frame. And you see over here that I'm calling Inception, 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 Inception. So the same function is being called, and I get an error. Now, back in the day with Chrome, it wouldn't give you this error, and the browser will eventually just crash. But in order to prevent the browser from crashing, if it reaches a limit, it's going to print out this error saying, hey, you've just created a Stack Overflow. How cool is that? All right, so that's one way to cause problem with our call stack. That is one of two places that our JavaScript engine works. But what about the memory heap? Is there a way to do something like this with the memory heap? Well, let's find out in the next video. Welcome back. Okay. I may have lied a little bit. Before we can talk about memory leaks, we have to understand this concept of garbage collection. JavaScript is a garbage collected language. That means when JavaScript allocates memory, let's say within a function we create an object and that object gets stored somewhere in our memory heap, automatically with JavaScript, when we finish calling the function and let's say we don't need that object anymore, it's going to clean it up for us. So JavaScript automatically frees up this memory that we no longer use and, well, collects our garbage, just like this. So only the data that is still useful to us remains. So that this way, we make sure we don't use up all the memory we have available because, as we know, memory is limited. How nice is that? Now, in garbage collected languages like JavaScript, the garbage collector frees memory on the heap and prevents what we call memory leaks. That is, when the memory gets too big until we reach our maximum size. Kind of like we did with Stack Overflow. But that is hypothetically. There's no perfect system, right? And garbage collection gives us a false sense of security that, oh, we don't have to worry about memory management. Because this garbage collection is done automatically and it's smart enough to figure out what we need and what we don't. But again, this is actually a big mistake. It gives JavaScript developers the false impression that they can choose not to care about memory management. And as you'll see, there are ways to actually make mistakes where the garbage collection won't actually free up the memory and you still have little pieces of boxes here that don't have any reference or don't point to anything really that are still hanging around. Now, in low-level languages like C, you control garbage collection and you tell it to remove parts of the memory. Now, that's very, very dangerous, but it's also the reason that programs like C are extremely fast and memory efficient, because you control garbage collection, and with that control, you can make it really, really optimized. So how does garbage collection actually work in JavaScript? Well, it uses something called mark and sweep algorithm. And this is a great video that shows how it works. Imagine on the left here are variables that we have in our program. And these variables point to different objects. And perhaps an object points to another object, and so on and so forth. And as soon as we remove that reference from that object, well, it should get deleted, right? For example, object 5, we don't need anymore because nothing is linking to it. So if we run this, we mark what we need, we sweep what we don't. And that's how garbage collection works. If we look at this through code, we can simply show that in action by using human over here in our object. If I all of a sudden, and let's change this to a var so we can assign it something else, and we'll say that var or human now equals 5, well, this piece of memory that is my name, first name and last name, is still in the memory heap, but we don't need it anymore. Nothing is referencing that piece of code. Or perhaps this human variable was just inside this function. And once this function is done executing and it's popped off the stack, well, we don't need that variable anymore. So the garbage collector is going to mark and sweep and clean this from memory. And now that we understand how garbage collector works, we can take advantage of this and show you how memory leaks happen. I'll see you in the next video. Bye-bye. Welcome back. Let's create our own memory leak. How can we do this? Well, the easiest way to do it is to just create an array, and we'll say that it's an empty array to start off. But within here, we're going to create a loop. Let's say I equals to 5. And I want you to keep looping as long as I is greater than 1. And I'm going to say I++. That means let's increment I by 1. Now, you see here that I'm creating an infinite loop because, well, I is always going to be bigger than 1. So all I have to do here is say array.push. And we're going to add to the array I minus 1. Now, when I run this code, what's going to happen is we're going to run an infinite loop that keeps pushing to the array I minus 1 over and over and over until, well, we fill up our memory and there's nothing left for us to use and, well, we're going to crash the browser. Let's see how this happens. Once I press enter. All right, things are happening. Oh, did you see that? Something went wrong while displaying this web page. We just crashed our browser. Go ahead and play with that if you want, or try to create your own memory leaks. But what I did was I filled up our memory heap with more and more and more data. The garbage collection wasn't really working because, well, we had this array. We were using this array over and over until we crashed our program. So memory leaks are pieces of memory that the application have used in the past but is not needed any longer, but has not yet been returned back to us, to the pool of free memory. Now, this was a silly example and most likely you're not going to do in your programs, but there are 3 common memory leaks that happen that I want to show you so you can avoid them in your application. The very first one, and this is something that you've heard over and over, and that is global variables. One of the reasons that we don't want to have too many global variables, such as doing variable a equals to 1, well, I've just added variable a as a variable on our global scope, something we'll get into a little bit later. But if hypothetically I just keep adding variables to my environment, well, we're adding more and more pieces of memory. And if these were objects and deeply nested objects, you can see the memory being used up more and more and more. Another one is event listeners. So if I have something like element equals document dot get element by ID in our browser, and let's say I select the button, and with this button I'm going to add an event listener that's going to listen on the click event, and it's going to do some function that, well, I'll just call it on click. We don't really have it here, but it's going to have that. Now, this is one of the most common ways to leak memory, and that is you add these event listeners and you never remove them when you don't need them. So that you keep adding event listeners, and because they're just there in the background, you forget about them, and next thing you know, you create a memory leak. This happens a lot, especially if you go back and forth between single page applications, where you're not removing the event listeners off the page. And as the user goes back and forth, the memory keeps increasing more and more as more event listeners are added. Another common one is simply using something like set interval, where you have the set interval function that does something, and inside of here, you start referencing objects. And these objects in here are going to, well, never be collected by the garbage collector, because this set interval, unless we clear it and stop it, is going to keep running and running and running. So memory leaks are something that we have to be careful of. So one example is SoundCloud. You see, SoundCloud, which some of you may know, you can listen to some really interesting artists and music. Well, they had this application that worked on a gaming device, but it was built with JavaScript and web tools, so that this SoundCloud application can be run in the background of this game console. What they found out is that they had a memory leak. Because people put SoundCloud in the background, it just kept running for long periods of time. So that this memory leak that they had kept increasing more and more and more, because people wouldn't close the application for, well, sometimes hours and hours and hours. And they noticed that they had a memory leak in their program because, unlike most websites or apps, their app runs a really, really long time in the background. So they had to fix that memory leak. I'll leave a link to this article where they explain some of this problem. It's really, really interesting if you want to learn a little bit more about it. Just something to be aware of, that memory is limited. That is, when it comes to call stack and memory heap, those are two places that JavaScript remembers or stores memory. And we have limited use of them. So for us to write efficient code, we have to be conscious to not have Stack Overflow or a memory leak, and to manage that memory well. All right, that's enough for now. Take a break, drink some coffee, have some tea, and I'll see you in the next video. Bye-bye. JavaScript is a single-threaded programming language. What does that mean? Well, being single-threaded means that only one set of instructions is executed at a time. It's not doing multiple things. And the biggest way to check that a language is single-threaded is, well, it has only one call stack. This one call stack allows us to run code one at a time. We're never running functions in parallel. As you saw, the stack keeps growing as we push new functions on the stack, and then we pop them one at a time. Now, initially in 1995, when JavaScript was born, this made things easy for implementation and for developers using the language, right? Because JavaScript was only initially a language useful for adding interactions on a web page, such as form validations or clicking a button, nothing really required having more than just a single thread. A good way to think about it is like this. Single-threaded means I'm the JavaScript engine and I'm eating with one hand, putting food in my mouth, that is the function, and then use that same hand to grab the next food when I'm done chewing my food. I can't put any more things in my mouth until I'm done chewing, and I also can't grab any more food until I finish chewing. It's single-threaded, one thing at a time. And because of this, JavaScript is synchronous. That is, one at a time in order that it appears, only one thing can happen at a time. You might be asking yourself. That doesn't sound super fast, does it? Let's tackle that in the next video. Bye-bye. What problems do you see with synchronous code? Think about that for a second. Pause the video if you need to. Ready for the answer? Well, with single-threaded, synchronous code that JavaScript engine runs, it's going to make it really, really difficult if we have long-running tasks. What does that mean? Imagine we are running Twitter. And Twitter, well, it's an application that we can tweet, we can check other people's tweets, we can look at followers, our tweets, our notifications, our messages. Imagine if they had a function that had, let's say, a really big loop that takes 5 seconds to complete. When that happens, if we just use the JavaScript engine, well, I wouldn't be able to click, I wouldn't be able to scroll, I wouldn't be able to do anything. A classic example of this is the alert function. If I run alert hi, my JavaScript is running right now and I can't scroll, I can't click anywhere, the website is frozen in time until I take some sort of action. And this mimics a long-running JavaScript, right? On the call stack right now, we have something like a function that's running. And until that call stack is empty, I can't really do anything. That's terrible. Why would anybody use JavaScript then? I mean, it's just going to slow our pages down, right? Well, here's the thing. I haven't been completely honest with you. That's because when we talk about JavaScript, most of the time, you're never just using the JavaScript engine, which is synchronous. We need to introduce the idea of asynchronous code. And in the next couple of videos, we're going to talk about what's actually happening behind the scenes, where it's not just the JavaScript engine that's running our code. We have something called the JavaScript runtime. And as we'll see, Node.js will also implement something similar. Because in order for us to write code that we can use in this modern day, we need something beyond just the JavaScript engine. I know, we're almost getting there to our complete picture. Hang in there because this is going to be a fun one. I'll see you in the next one. Bye-bye. Welcome back. It's time to talk about this diagram that looks a lot more complicated than it actually is. The JavaScript runtime. Since, as we mentioned, JavaScript is a single-threaded programming language, it has only one stack and one heap. Hence, if any other program wants to execute something, it has to wait until the previous program or function is completely executed. And if I do something that takes a really, really long time, well, things are going to be really slow for our program. That's not good. Boo, that's not nice, is it? We don't like that. And this is where JavaScript runtime comes in. In this case, the web browser is working in the background while the synchronous JavaScript code is running. And it's using something called the Web API or the Web Browser API to communicate and let the JS engine know, hey, I'm back with some data, some work that you told me to do in the background. Let's dig deep into this topic. The Web API comes with the browser. Chrome, Microsoft Edge, Safari, Firefox. All of them have their JavaScript engine implementation, and all of them have a JavaScript runtime that provide a web API. These web APIs are applications which can do a variety of things like send HTTP requests, listen to DOM events, maybe click events on a DOM, delay execution using something like set timeout, can use set interval. It can even be used for caching or database storage on the browser. Let me show you what I mean. If we go to the console here and I look at the window object, well, this is what the browser provides. This is the web API that we can use. So that if I scroll down here, I can see different things that the browser provides for us that our JavaScript engine can use. For example, if I scroll down to, let's go to fetch. Fetch, that is the function to make HTTP calls. We can use that. If I keep scrolling down, and let's look at something fun like indexed.db or IndexedDB. That's actually a little database that we can use on our browser. If I go to application here, I see that I have some storage and IndexedDB that the browser provides for us. Very, very cool. If I keep scrolling down, I also see something familiar to us, such as set timeout. Let's see, where is it? Right here. Set timeout, set interval. All of them are provided by the browser. They're not native to JavaScript. So remember that the browsers are helping us create rich web applications so that users aren't just sitting around waiting for our JavaScript to execute. Anything that can be offloaded, they'll take care of that for us in the background. Because you can imagine, if the browser had to use the same JavaScript thread for execution of these features, well, it's going to take a really, really long time. So browsers actually, underneath the hood, use low-level programming languages like C++ to perform these operations in the background. And these APIs are called web APIs because, well, they're APIs provided by our web browser. And these web APIs are what we call asynchronous. That means you can instruct these APIs to do something in the background and return data once it's done. Meanwhile, we can just continue working on our JavaScript call stack and execute functions. So what are these other two things? Now, we're only going to scratch the surface here because towards the end of this course, we have an entire asynchronous JavaScript section. But this is what happens underneath the hood. We have items on the call stack, and as soon as something comes up, like set timeout, that's not part of JavaScript, it's part of the web API, the call stack is going to say, oh, I have something that's not for me here, it's for the web browser, for the web API. So it's going to say, hey, web API, here it is. I don't know what to do with this. You take care of it. The web API is going to say, I know what set timeout is. Let me take care of that and do that in the background. Now, with set timeout, you usually want something to happen afterwards. So once the web API is done working on it, maybe it's fetching some data from a server, it's going to say, all right, I'm done with this work. Here's the data, and here's perhaps a callback of what I want you to do with that data. And then the event loop is going to say, as soon as the call stack is free, is going to say, hey, I have something for you here. Would you like to add it onto the stack? And if the stack is empty, it's going to push this callback onto the stack. But that's kind of confusing. Let's actually code this and demonstrate how it works. Imagine we had a console.log, and in here we'll just print 1. And by the way, this is a really, really common interview question, so hope that catches your interest. And let's say we'll also do set timeout, which is part of the web API. And in here, we'll just give it a function, and we'll just say console.log 2 in, let's say, 1,000 milliseconds or 1 second. And then console.log 3. Now, if you've been working with JavaScript for a while, this isn't difficult. You know what's going to happen. But just to go over it quickly, if I go to my browser here, let's copy and paste this, and I run it, I get 1, 3, 2. Why is that? Well, it's because we added console log to our stack, and we logged onto our console, and then we removed that call from our call stack, and then we went to the next line, set timeout. We added this onto our stack, and then immediately the JavaScript engine is going to say, oh, set timeout, that's a web API. I don't really care about it. I don't know what to do with it. I'm going to just send it off to the web API. So this gets moved away from the call stack and gets sent to the web API. Now, we don't know what's happening on that side of things, but we just go to the next line and say console.log 3. It's going to log 3. Now, behind the scenes, the web API is going to take the set timeout. It's going to start a timer that is going to run for 1 second. And once that 1 second is over, it's going to push the callback. That is, what to do once it's done running for 1 second. And the callback in this case is console log 2. It's like it's calling us back saying, hey, we're ready for you. 1 second has passed. Can you console log 2? And what happens now, the console log 2 goes to the callback queue. Let's go to the diagram. Goes to the callback queue and says, I'm the first person that's done. Can you console log 2? The event loop is a loop that's constantly running that's saying, hey, is the call stack empty? Is the call stack empty? Is the call stack empty? And the event loop only runs once the call stack is empty and the entire JavaScript file has been read. In our case, console log 3, no matter how fast the web API responds, adds the console log 2 to the callback queue, the event loop won't start putting anything back into the call stack until the call stack is empty and we've run through the entire file at least once. So in our case, after console log 3 gets printed and popped off the call stack, the event loop is going to tick and say, all right, can you console log 2? And that's why we get this weird pattern. Now, Philip Roberts, who has an amazing talk about the JavaScript event loop and this whole JavaScript runtime system, created this tool to actually visualize this a lot better than I could explain. We're going to go over the same steps that we just did. We see that we have function A that calls function B that calls function C, and function C that calls set timeout. That's a web API. And it's going to have a callback function that is, once it's done running for 3 seconds, call achieve nirvana. And achieve nirvana is going to console log you are enlightened. Let's see what happens. And before I click play, see if you can predict what's going to happen and to test yourself. Let's have a look. So we see right away, A gets called. That's the very first thing that happens because up until now, we've just declared functions and we only run on line 17. That is, we execute function A. So function A gets executed and we call B. So we add that to the call stack and then we resume call C. That gets added to the call stack and then C gets called. That is, we add set timeout to the call stack. And what do you think happens here? Well, set timeout now gets sent to the web API because, well, it's a web API. And we don't really care what the web API does with this. It has its own implementation. But in this case, it's using this timer to just run for 3 seconds so that it can add it to the callback queue. But in the meantime, our JavaScript engine doesn't care what's happening. It's just going to keep working on the call stack. So if I resume here, you'll see that A, B, and C all get popped off the stack while the timer is running. Now see what happens when this timer ends. I'm going to resume, and look at that. It finished in 3 seconds, so it's going to put it back or put it into the callback queue. And the callback queue is going to say to the event loop, hey, can I come back to the stack? I'm lonely. Can I come back to the stack? And the event loop says, hold on, let me check. Is the call stack empty? Yes, it is. Has the entire file been run? Yes, well, line 17 is the last line. So that's the last thing that we want to run. Okay, you're allowed to go back on the stack. So I'm going to resume, and look at that. The achieve nirvana is going to get popped or pushed onto the stack. Console log gets printed, and then we pop everything off the stack. Congratulations, we've just achieved nirvana. That's not too bad, is it? Now, here's a fun little question for you. What happens if we do the exact same thing, but this time add 0 here? What do you think will happen? Well, if I run this, I get 132 still. Now, like I said before, this is a very common interview question. The reason that happens is that no matter how fast this set timeout timer happens, it still gets sent to the web API, still gets sent to the callback queue, and the event loop still needs to check those 2 checks. Hey, is the stack empty? And has the entire file been run? In our case, no, we're still waiting on console log to run. And only then will I push our callback function, our console log, to our call stack. How cool is that? And using this method, we're able to have this power of asynchronous code. That is, instead of being limited to one call stack and one memory heap, whenever we get tasks that can be asynchronous, that take a long time possibly, like modifying DOM or making HTTP requests, well, in that case, we can just send that off to the browser. The browser can just run that in the background, and whenever we're ready, it can just use its callback queue and event loop to notify us. All right, that was a long one. Let's take a quick break, and I'll see you in the next video. Bye-bye. Welcome back. We've done a brief run-through of the JavaScript runtime and asynchronous JavaScript. Now, this is something that we're going to get into a little bit deeper later on in the course, but I hope by now you should have a good understanding of the difference between a JavaScript engine and a JavaScript runtime. The way that I like to think about it is like this. You see, a JavaScript file is kind of like musical notes, ways for us to write music, write programs. The JavaScript engine is kind of like the musician or the composer. That person is the one that can read this music and understand it and make sense of it. And then the runtime is kind of like the whole package where we have the musician, but we also give that musician, besides the musical notes, all these tools to play our beautiful music. So let me ask you this. If we're able to have different JavaScript runtimes because, well, JavaScript can run outside of the browser, what do you think Node.js is? Well, is Node.js a programming language? Is Node.js a JavaScript engine? Is it a runtime? Well, this kind of gives it away. It's a JavaScript runtime. It's not a language. It's a runtime. You see, up until 2009, you ran JavaScript code inside of the browser. That's why people didn't really respect JavaScript. They thought it was a silly toy language. Well, Ryan Dahl in 2009 decided it would be great to run it outside the browser. Because up until now, we only had that runtime, that web API and the callback queue and the event loop, all browser-based. So he created Node.js, which is actually a C++ program. You can actually think of it as node.exe. It's an executable, right? A C++ program that provides this runtime for us. And if we look at the Node.js runtime, you see that it looks quite similar with our browser-based runtime, doesn't it? When it comes to Node.js, there are a few differences, but it works the same way as our diagram. We have our V8 engine, and then we have our event loop and what they call our callback queue. And they use something called libuv, which again is written in C++, for us to do these asynchronous operations with the V8 engine. Now, when it comes to Node.js, it does a little bit more than our web browser runtime. You see, in the case of a browser, we're limited to what we can do in the background, right? The browser isn't going to allow us to do much on the person's computer. You can't really access, for example, the file system of the user. I mean, that would be a huge security flaw. It just runs on the browser on the tab that we're currently on, in what we call a sandboxed environment. But in Node, we can pretty much do most of the things in the background. We can access file systems. We can do all sorts of things. You see, Node.js uses the Google V8 engine to understand the JavaScript, but it uses this libuv library, which works along to create this event loop to extend what we can do in the background. Now, here's the fun thing. If I install Node.js on my computer, and let's just run Node, if I type in window here, well, I get an error. There's no window like we had in the browser. Instead, Node has something called global, and that's its global API. You see that just like we had with window, in Node we have this global API that we can use, which also happens to have set timeout, set interval. That's nice, but also has some extra things that we couldn't do in a browser. And that is why Node is set to be a server-side platform based on asynchronous I/O that is non-blocking. It means that it uses JavaScript, but outside of the browser, but it creates this entire environment, this runtime that runs outside of the browser, and it allows us to have the same model of a single-threaded model, but any asynchronous tasks can be non-blocking. That is, they can be passed on to what we call worker threads in the background to do the work for us and then get sent back through the callback queue and event loop onto the stack. We were able in 2009 to have a different model to perhaps create servers. You see, back in the day, we would create a thread for each request. Something like PHP would work like this. And if what we call the thread pool, that is, however much the server can work, is maxed out, well, the requests would just have to wait for the other ones to be available again. Node.js changed this mentality and said, hey, we only have this one single thread. But as soon as you give me a thread, I'm just going to pass it off to my asynchronous runtime to take care of it. And this simplified things a lot. Now, there's pros and cons to each method, but I hope now you see the power of the runtime, how it adds on this extra feature to JavaScript so that we can finally have the capabilities we had in the browser, but also the capabilities outside of the browser. I'll see you in the next video. Bye-bye.